Now, let's try to understand the empirical Bayesian credibility theory model, or in short, called as EBCT Model 1, which in a way is an improvement over the regular Bayesian credibility models with some similarities and some kind of differences that are existing between them. The concept of this empirical Bayesian credibility theory, they based on that particular concept, as the word itself is saying, they are more empirical kind of methods. They have been derived by observations of the data rather than any specific assumptions of the prior distributions. In a regular Bayesian credibility models, we know that the prior distribution of the parameter is known in advance, whereas here there is no such kind of an assumption regarding the prior distribution of the parameter. So under this concept, different kinds of models have been created, and one of the most commonly used models in that particular category is the Model 1. So here we'll try to see what are the key differences that are lying between this empirical based credibility theory model and that pure based credibility mechanisms that we already know. Here, to go more into the specifics, even this EBCT model 1 in generally is called as a generalized version of normal model, normal Bayesian credibility model. We'll see why it is. See, but a simple thing here, a few assumptions on which this model depends on is the individual, the claims in each year. So probably if I talk about claim or frequency, the claim amount in each year, yes, it is depending on a parameter theta. It follows the claim amounts each year follow some kind of a distribution based on the parameter theta. This value of theta is fixed but is unknown, and it may be same for all the xj's. And given the value of theta, the moment I know some value of theta, we say that the xj's are completely independent and identically distributed. Some of the basic assumptions. So the theta, whatever we are defining, which is the risk parameter, in this case, it could be a direct real number, some number, or it could be a set of numbers. And simple conclusions from there, whatever are my xj's, which are the claims in each of the years. One, they are identically distributed. The distribution is the same, right? All of them will follow a similar distribution, but they are conditionally independent only given the theta they are independent. So unconditionally they need not independent means xj can very well depend on xj minus 1 and so on. Now this is one major difference between the regular pure Bayesian model and the empirical Bayesian model. Here we are introducing m theta, which is expected value of xj given theta. Earlier, if you remember, the regular Bayesian models, especially the normal model, it has considered this as theta itself. Whereas in this model, it's a function of theta. Right? Similarly, another parameter s squared of theta comes out as the variance of xj given theta. See, if theta is known, the xj's are independent, identically distributed, but neither this or this, you see that there is a impact of J at all. There is no impact of J in either of them. So these two are independent. I mean, the xj's are independent, which is very clearly coming out from there. And one more important context is theta wise, it's a random variable. So even our m of theta as well as s squared of theta also should be our random variable. Now look at the way we are comparing these two models. Probably I want to look out between the empirical Bayesian credibility theory model 1 as well as the pure Bayesian credibility theory model. Whatever the theta, whatever is the parameter for the underlying claims, we are talking about in a similar context for both of them. Underlying distribution for the claims, whatever is the distribution, the claims are total claims are following. That is what we are saying, it is following a parameter theta, which is more or less the same under both the mechanisms. Similarly, whatever the kind of assumptions we have made regarding the unconditional distributions, we said all xj's are identically distributed. That is still the same, but they need not be unconditionally distributed. They need not be unconditionally independent, right? So xj need not be same as xj plus 1. They need not be unconditionally independent. But from a conditional perspective, given a particular value of theta, both the models are saying they are all independent, right? But this is where the differences are coming out between the two models. Now, when you talked about the conditional expected value of xj given theta, this model, because it being a normal kind of a model, the mean was theta itself. Whereas here we are talking about it as some function of theta. Similarly, the variance of xj given theta, if you remember, we have taken it as a fixed sigma 2 squared. Whereas again, here it is some kind of a function of theta itself, s squared of theta. So this is where this is a random variable here, whereas here we are fixing some kind of stuff. And in the normal model, regarding the parameter theta, we have started off very clearly that the theta is following a normal distribution. So we have started off with a prior parameter for prior distribution for the parameter. Here, no assumption regarding the distribution of the parameter is considered. And in case of a regular model, here the theta is a real number. But here it could be any kind of a general quantity. It could be a set of numbers. It could be a range of numbers as well. So that's what brings out the differences between these two models. And when I have to go with, once I am able to compute m of theta given x, so the estimate of this m of theta given x comes out simply as 1 minus z times expected value of m of theta plus z times x bar. So this is again coming out as a credibility estimate, and z comes out as n divided by n plus expected value of s squared given theta divided by the variance of m theta. We'll take a simple example wherein once we do a few calculations, it becomes quite simpler for us to really compute what all these numbers are, and an understanding of an example will simplify how this model is going to be used for the credibility theory building purpose, right? So for that purpose, let me take a 6 years data, right? I'll talk about claim amounts. So I'll say year 1, year 2, let's say I'm taking it over a 6-year period. For the last 6 years, I am observing the data for, let's say, 5 different lines. right? Similar products. I'm looking at 5 similar products and trying to capture. Here I am not having any prior distribution or anything. Everything is derived from the data. So that's the reason I am working out with 5 different sets of data, and let's say a few numbers associated with each one of them. So let me have some kind of numbers with each one. Right, those were the claims of product A. Then we have B, right? A good understanding of the example will simplify the whole understanding, because the mathematics here becomes more and more tougher. So a practical example can give us a good insight in terms of how can I use this empirical Bayesian credibility model to typically build my estimate, and what is the kind of credibility percentage that is going in each of the scenarios. Right, this numerical probably if we focus heavily, probably any kind of practical problems, once we are able to capture the real world data of different kinds of collaterals, we can very well work it out. Okay, so these are the five different products, similar products, for which I have collected the data over a 6-year time period. Probably this is the most latest and this is the most oldest. Now, here I will compute a few things. These few calculations which I am more interested in is one, I'll have xi bar, right? I'll have it as xi bar, which is nothing but the average of each of the product across all the years. So I'll take the average of each of these product across all these years. So which is nothing but sigma xij divided by n. So this is working out to 1375, and that way I can find out the average of all. And I can very well add up this averages, the adding up of all these averages, which is nothing but, if I am looking at the total claim amount per year across all the products put together, if I am more interested in the average claim amount per year rather than looking at average claim amount of A or B or C or D or E, if I look at average claim amount per year, it works out to 18,675. Then what I'm also looking at is each individual item. I'm looking at the computation of the average variances, right? Average variances of within each, what is the annual average variance? So average variance, if I am looking at, so I could very well take each observation, I'll subtract the mean of that particular observation, right? I'll subtract the mean of that particular observation, and I simply do a square. Okay, each observation, right? I have to, each observation I am doing a subtraction of the mean and squaring it. Now this way, when I am looking at for 6 of them, I'll get 6 different values, right? The same logic probably I can continue it across, which means overall I can take the average variance. Here I can very well compute, which is nothing but, here I have taken sigma xij minus x bar of each I have squared it over all the j's, right? So this is working out to the summation. If I am looking at, in this case, it's working out to some 9,973,000. and probably when I'm going further, these are the numbers that are working out. And finally, I can even sum this up as well. So this summation working out to some 53 million. So here I am looking at the variation within from its corresponding mean for each of the observed data sets. Then the third thing which I will try to bring out is the variation within the mean itself, within the means of everything. So I'll take one mean which is uniform across, first of all, right? I'll take the mean of this entire data. So what is the mean of this entire data if I take, which I call as x bar, right? Let me call something as x bar. The x bar is coming out simply as this divided by 5, right? So this comes out to be the mean. Either I could have taken it as a simple average of all these numbers, which should work out to the same, or I have taken this by this. So this is x bar. Now what I really want to see is what is the kind of variance that is there between the various means. So the first one is having a mean of this much, second this much. So what is the kind of difference in the means that is existing? So which is what we call as xi bar minus x bar squared. I am taking it as xi bar minus x bar squared. So if I am considering this, xi bar is this much minus x bar is this much. I am taking it as a square. Okay, so this is what is one more set of numbers that are working out, and a summation is giving me, in this case the summation is giving me this number. Okay, so just going further now, taking it into our credibility theory. Now, especially when I want the expected value of m of theta. So, expected value is coming from all the observations taken together. So, expected value of m of theta comes to 3735. Then, expected value of s squared of theta. Right? What is the expected value of s squared? I can take this number, which is the squared across all their from their individual means, and I simply take it as 1 by n times 1 by n minus 1 times whatever is the individual j equal to 1 to 6 xij square xij minus x bar whole squared, which we have done. So xn is 5, small n is for 6 years, so I'll take it as 5. And this we have computed, which is this one. So the average of the fleet completely is nothing but I can take the average of this entire variances. Right? The average of the variances, I can very well take this number divided by 25. So the average of the variances, probably I should call this average of variances, is coming out to this much. And at the same time, so that is the estimate of s squared. So this becomes expected value of s squared theta, which becomes 2.156 million, 2156938. So this is expected value of x squared. Similarly, I can very well find out the variance of m of theta here. Now, the variance of m of theta comes purely from the perspective of 1 by n minus 1. 1 by n minus 1, the number of different entities that we have collected, multiplied by whatever is the mean variance that came between the means, this one. xi bar minus x bar squared minus 1 by n times whatever is the expected value of s squared theta, which is nothing but expectation of x squared minus expectation of x whole square. So this logic is very much working out as, so this number I divided by 4, this number is divided by 4, and this number is divided by 6. Alright. So overall the difference is coming out as this number minus this number, which is working out to the variance between the means. Right, variance between the means is coming out to this much, which is nothing but v of m of the variance of m of theta. Now I have the expected value of s squared theta, I have the variance of m of theta, so I'll compute the z, which is the credibility factor, comes out as n divided by n plus expected value of s squared theta divided by the variance of m of theta, which in a way I can compute it as 6 divided by 6 plus expectation of s squared theta is coming out to 2156938. Variance of m of theta comes 3351748. So we can compute the value of z from there, which comes out as 6 divided by 6 plus expected value of s squared of theta is this much divided by the variance of m of theta is this much. Works out to z being this much, which means my 1 minus z goes out as 1 minus of this, working out to this much. Now this is where I can very well go ahead with the credibility estimate. Now what I am simply taking is I am taking z times whatever is the mean that came. Let's say now I am doing the credibility estimates for each one of them. For all these 5, one by one, I am doing the credibility estimates. Now this is where probably when I have to do the credibility estimate, I am taking a z value multiplied by whatever is the x bar corresponding to this xi bar plus 1 minus z times, right, 1 minus z times whatever is the overall mean that has come up. So which is giving me that for this the credibility theory based estimate is going to be this much, and I can repeat the same for all the 4 elements as well. So this is how we are using the empirical Bayesian credibility theory model. Here we did not use any kind of priors or posteriors or likelihoods. We have simply gone ahead by looking at the observed data from 5 different kinds of products, which are assumed to be more or less similar in behavior with respect to the risk which we have to really estimate. Based on that, tried computing the expected value of m of theta, expected value of s squared theta, which is the variance from the mean corresponding to each of the entities. And then we have looked at the computation of variance of m of theta, which is purely based on the differences of the means from the overall mean. So all these are typically contributing to coming out with a credibility premium as well as a credibility estimate also. All right. So this is the typical way out to understand the empirical Bayesian theory based credibility estimate. And what we could clearly see, just like in any other case, the z value always lies between 0 and 1. Some of these things which are very much similar, and because of this formula it's an increasing function of n. as n increases more and more, right? The more the data we are having from the risk itself, the more is the credibility, the more is the reliability, which results in Z value increasing drastically. And if the expected value of S squared theta is lesser, what does that mean? The variation within each of the observations. The variation within each of the observations is much lesser, right? Probably then this ratio is going to be much lesser. So the denominator is going to be much lesser. Denominator lesser is resulting in a higher value of z. So if this is I mean the reliability, if this value is much lesser, probably I have to give more and more reliability to my data itself. This value is lesser, overall this is lesser, so this value is going to increase for me. So and so that's the reason we say z is a decreasing function of expected value of s squared theta, but it's an increasing function of variance of m of theta. If m of theta's variance is much higher, means the different means that are generated by the different observations, different products that I have observed, it's drastically different. That means because of lacking of consistency in my collateral based data, the weightage that goes to the overall mean would be much lesser, and more weightage would be given to my own data. As we have seen in the example here, the variance of m of theta is much higher, as we are seeing that there is a heavy deviation. The overall mean is 3375, but individually we have the means right from 1300 to 6000. There's a huge variation. That's the reason the variance of m of theta is much higher compared to s squared of theta. If you are looking at the s squared, expected value of s squared of theta, this is only around 2.15 million, whereas variance of m of theta is around 3.6 million. Now, because of that, more weightage has typically come out to the observations from our own risk itself, rather than looking at all the competitors and packaging them as a part of our overall estimate, right? So this is how your empirical Bayesian credibility theory model will help us, just by looking at the various observations, coming out with a very confident, reliable estimate of the claims or the premiums or something based on the data. All right.